Well, this is a short video on acyl addition reactions or nucleophilic addition reactions, where the focus will be back to the carbonyl we go with some nucleophile at some point attacking the carbonyl, whether it be after protonation of the O or if this is a good nucleophile before protonation of this oxygen. But the difference will be in this reaction as compared to the few that we've already looked at is that we will not have a leaving group at either of these positions. If it's just an alkyl group or a hydrogen on both sides would be formaldehyde, but an alkyl group or an alkyl group or an alkyl group and a hydrogen. In other words, if there's no leaving group, nothing that can be protonated, no halogen, just alkyl groups or hydrogens, then we have an addition reaction. An addition reaction. Now we'll look at some chemistry beyond the just initial addition reaction, wherein we take the addition product and we'll start to remove this oxygen in the carbonyl. But that is not acyl substitution. That's addition and then elimination of water. So it's addition with a subsequent elimination. So that'll be the focal point of this video and two others, is taking and reacting nucleophiles not with class 1 carbonyls, that's with leaving group, but class 2 carbonyls, where we have alkyl groups or just hydrogens off of the carbon in the carbonyl. So this video will look at three types of strong or weak bases that can be used, not in acid solutions. We don't want them. If we had them, we'd kill these reagents. But in base conditions, Grignard reagents, cyanides, and hydrides adding to a carbonyl. So that's what we'll look at, and in the second video we'll flip and go to sort of acid conditions to help these nucleophiles, which are very weak in their basicity, and on this one also, and the amines. We're going to, in all of these, use slightly acidic solutions. Slightly acidic solutions to help catalyze the reaction. And we'll look at that in the second video, where we'll have not just initial addition, but we'll have the potential to take this oxygen and do some elimination of this oxygen off as water, where we don't just cap with a proton and stop at addition. We'll go on and do more than just addition. That'll be in the second video. And in the third, we'll look at special types of reactions involving ketones and aldehydes, those that do not have leaving groups, just R's and H's. The Wittig reaction, kind of pronounced with a V, and the Wolff-Kishner reduction. Let's get into it. And to do that, I'd like to maybe just review a little bit of the basics, overview of carbonyl chemistry or acyl addition, acyl substitution. Regardless of whether we're going to attack a class 1 carbonyl or a class 2 carbonyl, that is without leaving group. These are the aldehydes and ketones. These are the acyl halides, anhydrides, esters, carboxylic acids, amides. Regardless, the first step as part of the nucleophile attacking was to have it attack the carbonyl and advance the electrons up to the oxygen. That's going to be seen in this video also, is that we are going to take a nucleophile and attack the carbon in the carbonyl. I do want to point out, though, as we finish these three videos, we'll be getting into reactions of strong bases, not with the carbonyl only. That can happen. We need to consider that. But in polar reactions, you often have to consider two possible reactions. You often have to consider, and I'm just going to put some X here, and I'm going to leave these undefined. Let's call it D and E. We haven't defined what these are. In polar reactions, you have to look for, if you have a strong anion and you have some electrophile that could be provided in this reagent here, you often have to ask these two questions. What can I do acting as a nucleophile? What could I do acting as a nucleophile from this negatively charged species to this carbonyl containing species? That's number one. And two, what could I do if I was acting as a base? Because we have in many cases, these two reactions competing against each other. So as we move into, I guess what we'll have is the green arrow, where the nucleophile attacks the proton on a carbon next to a carbonyl, don't think, well, it's either one or the other. It can be both. But we just have to see which one's going to get us to a lower energy product. We have to always remember in polar reactions, our negatively charged species needs to be considered in the, I guess, act of working as a nucleophile attacking a carbon, or considered as acting as a base and hitting a proton. You usually have to look for those two possibilities. Let me put up as a bit of review the reactivity order of both class 1 and class 2 carbonyls, because we have to kind of put the class 2s in, and I want to put them in right at this point. Aldehydes and ketones. Aldehydes have one hydrogen off of that carbon in the carbonyl, and a ketone has two R groups off of the carbon in the carbonyl. Aldehydes and ketones slip in between acyl halides and hydrides next in order of reactivity. I'm just sort of order of reactivity in general with any nucleophile, whether it act as a nucleophile or base. These are most reactive. Second is the anhydride. Third and fourth are the aldehyde and ketones in that order, and they're dang close. I mean, they're really similar in reactivity. And then we have the carboxylic acid and the ester, which are the same because they have the same sort of donating group next to the carbonyl. And then we finish with the amides. That's sort of the reactivity order, going from least reactive amides to the esters and carboxylic acids. These are the same. And then we have the ketone aldehyde, and then on up the chain, anhydrides and acyl halides. That's the combination of both the class 1 and class 2 carbonyls. Their order of reactivity to what? To something negative floating around in solution that could act as a nucleophile or act as a base. It's important to remember that its reactivity of the carbonyl is reflective of the reactivity of the acidic proton. So if we have a very partially positive carbon here, if there was a proton here, it would be very acidic. So we can really follow this order of reactivity regardless of whether this acts towards that carbonyl or acts towards the proton. Acyl halides are more reactive. Regardless of the negative charge acting towards the carbonyl or to the alpha proton, the anhydride is more reactive than the aldehyde, ketone, carboxylic acid, ester, and amides. That's important to remember. So you can start picking which functional group to take your negative charged species and react it with. Now let's go ahead and look at the details of the aldehydes and ketones and how they react with nucleophiles. I've shown the nucleophile here as sort of a blue ball, kind of a wrong color, I guess. It should be red. But if we attack as a nucleophile, attacking a carbon, we usually come in not in an SN2 manner, but sort of off the angle from the planarity of the carbonyl. So we come in a little bit cheating towards the carbon side relative to the oxygen here. This is the CO double bond. We come in at a slight angle sort of above and below the plane of the carbonyl. This is just a hydrogen here, and this is just a CH3 that's going to the back here. So we come in a little bit off angle, and of course we would advance those electrons up to the oxygen. And it's just important to point out that whether it be for steric reasons or electronic reasons, we have more accessibility. If we look at sterics, this carbon here is in a ketone. We have two methyl groups hanging off this carbon, so it's maybe a little bit harder to get to this carbon. And second, these methyl groups are a little more donating inductively, so the partial positive charge on the carbon in the carbonyl is a little less significant than that over here. So not only one is the hydrogen, this little white ball, smaller, so sterically the site is less hindered compared to the ketones, And electronically, you can't give as much electron density to the carbon from a hydrogen as you can a methyl group. So the site here is more positive, more accessible and more positive. Less accessible, more hindered in a ketone, and the ketone has a, I guess, less partially positive charge. So this is applying to the ketone here. We're saying the ketone is more hindered, the aldehyde is less hindered. And the electronic effects, we also have to consider the aldehyde is more partially positive because it's not satisfied by the neighboring groups. This is more partially positive. This would be less partially positive. I'll use a bigger and smaller partial positive charge. All right, just in general, if we have two aldehydes compared against each other, benzaldehyde, and we end up with an Al if it's a aldehyde and a alkyl group, ethanal, we have two carbons, F for the two carbons, and then an alph. An al is indicating an aldehyde. If we had a ketone, those are going to end up with those are ending with a different name. This would be ketone that's you're knowing as acetone. That would end up with one as a last name, one. Aldehydes end with Al. I'll use those as we go, so you don't have to memorize them, just sort of learn them as you go. Well, benzaldehyde and ethanal, if we compared them against some nucleophile, something that has extra electron density, which one would be more reactive? Well, we look at the donation of this benzene ring to the carbon. If it donates, the partial positive charge goes down, and that's exactly what happens. By resonance, this can donate electron density to the carbon in the carbonyl. So it's less partially positive because we can have donation by resonance, and I'm just drawing the arrows that would get us started. That lowers the partial positive charge. It lowers it. Well, if it lowers the partial positive charge, then this is less likely to attack. So that's a way we can easily assess the reactivity of the carbonyl, is how partially positive is the carbon in the carbonyl. This would be less donating because it only is through inductive effects. It is slightly donating, but not as much as the benzene. So donating effects, and I guess we could put under that resonance. Donating effects of the benzene ring. All right, so I think we need to start now, since we've kind of covered how we attack and we've looked at following the partial positive charge to know what's most reactive. Let's go ahead and look at those three nucleophiles, the Grignard reagent, cyanide, and aluminum hydride, reacting with the aldehyde or ketone, and we'll be done. So the first one, I'm going to go ahead and draw 2-propanone, meaning we have at the second carbon in a 3-carbon chain, we have a ketone. So that's 2-propanone, also known as acetone. And we're going to make, if we react that with a Grignard reagent, methyl magnesium chloride, in a reaction, followed up on the second day subsequent to the complete reaction of the Grignard reagent and ketone, we follow it up with water in acid, we will get tert butoxide. Tert butanol. So we have that drawn here. So the mechanism goes like this, and you know you should always take your alkali or alkaline metals if they're bonded to an organic, and you should put a positive above them. And here we have a negative on the methyl group. Now I've drawn that positive charge over here, so I'll erase that and just say the whole thing here, we know if we have a magnesium, lithium, sodium, potassium, we can treat it as if it gave its electron to that R group. So we've drawn it with a positive, and the electrons that might have been in a bond are given to the carbon, as a lone pair. That gives it a negative charge, and then we can use that to a very strong base. We would not want to expose this to water. We can use that to attack the carbonyl in our propanone, 2-propanone. That gets us to a weaker base. Not a weak base, I didn't say that. we know O's with negatives are still strong, but C's, carbons with negative, are even stronger. So this is a downhill run. We have gone downhill in our first day's reaction, Grignard reagent, with a ketone. We've gone from strong base to weak base. You've let that reaction complete itself, Monday's reaction, and then you let Tuesday roll in. So on Tuesday we come in and work this up, and of course, since we have a full negative on that oxygen, it's going to satisfy itself with one of the protons in your acid, and we get a quenching of that oxygen. And you also, I didn't draw this, get magnesium hydroxides formed, as the magnesium would be, I guess, reacting with water, but we've left that out, just focusing on the organic moiety. All right, just a quick completion of the discussion. Why is this reaction not reversible? Mostly because this first step involved a strong base in the Grignard reagent, giving us a weaker base in our alkoxide. So we had a strong base to weak base conversion. And when you have that, you're going downhill. Already said that we were going downhill. So, of course, this is not reversible. Now, we can have similar reactions with the alkyl lithium salts or organolithium salts. These are called Gilman reagents. When you have a copper lithium salt, they're not as reactive. They're less reactive, but they still favor addition to the carbon of the R group bonded to the copper. Now, this is a more covalent bond here, and this is more ionic, where this is full negative. But either way, these R groups serve as nucleophiles to attack the carbonyl. And so also, if we have the sodium, we put a negative on this carbon in the acetylide, CCH3, we can have this carbon also attack as a nucleophile. The carbonyl, we'll just show that over here. We'd say sodium, lithium, potassium, group 2 metals bonded to something other than itself. It's practical just to show a positive on it and a negative to whatever it was bonded to. It's given its electrons. So it has a lone pair on this carbon, and we can attack then. The carbonyl start the process and see, oh, if I do that, I get my nucleophile attached to this carbon. In the second day's reaction, work up with an acid, and I'm done. Well, that's our first reaction, using a Grignard reagent, followed up with, on a subsequent day, addition of acid. Let's get to our last two, the HCN and cyanide, used together. We're going to have a buffer solution. We'll talk about why. We have to use a buffer solution. This is a weak base and a weak acid. That's what the buffer solutions are, as you know, is a weak acid with a weak base. So let's talk about why we have to do that. We can propose, since we have still basic solution, we have some cyanide floating around in solution. It's not just all HCN. So we have some cyanide floating around in this buffer solution that can attack, and that puts the negative on the O. Uh-oh, that's a stronger base coming from a weaker base. That's going uphill. That could be a problem. That's why we add to the sodium cyanide. We can't just have sodium cyanide because you'd end at this point after your day's reaction or your completed reaction. Well, we can't do that because this is stronger. It just kick this right back off to go to a weaker base, because we favor strong base to weak base reactions, not weak base to strong base reactions. So we're sitting at a higher energy right now. But no worry, we've added some HCN in this solution so that we can cap that oxygen, bring it down in energy, and regenerate our weak base. So we've basically, if you think about it, went from a weak base, the cyanide, to a strong base, the alkoxide, back down to the same very anion, the same weak base level. So what we really have to do then is we have to drive this reaction by having an excess of the cyanide. We have to use Le Chatelier's principle. And we have to have a little bit of HCN present so that we can bring it back down in energy at any point when we hit this part of the mechanism. We have to have some HCN left. Alright, so that's how that reaction goes, is we have a buffer solution. We want to drive it by having excess cyanide, so we can have addition in the end of HCN. H from the hydrogen cyanide in solution and the CN from the sodium cyanide in solution. So how would you kill this reaction? I've already pointed out this box here that the buffer solution is needed, and we can make it sometimes by just using sodium cyanide and adding to that sodium cyanide solution some acid to generate in solution a little bit of HCN. I should have pointed that out. But we want to make, let's say we want to work up the reaction. Well, it's only reversible if we have some of this HCN in solution that we can use to, I guess, protonate this oxygen. So we can do a couple of things, but here's just one. The anion needed for the reaction to go backwards or forwards would be the cyanide, because to go backwards we'd have to have it come in and take the proton to go back to the alkoxide. So what we can do is we can just work up in a slightly acidic solution of water with acid workup and just protonate all the cyanide, because then we don't have the alkoxide forming, and this was the sort of key step, was the alkoxide. So just adding some acid, quenched with acid, we can protect from the formation of this anion, which would then allow for this cyanide to be kicked off as a leaving group. We don't want that, so we don't want this to form, so we can just use some acid to quench that. So the anion that would be needed to drive this reaction forward or backwards, acting as a base, it would get us back to here, or acting as a nucleophile, it would get us here, is this cyanide. So if we just quench that with acid in water, we can stop the reaction, work up the organic product, and we're done. And that's our second one. Let's look at our last one, and we're out of here. So the last nucleophile, we've looked at Grignard reagents, and we can look at magnesium chloride, where the R was negative because it was attached to magnesium. We've looked at sodium cyanide, but we couldn't use this by itself. We had to have HCN because we'd get stuck at a strong base, so we had to have a buffer. Our last one is a hydride. Sodium is bonded to something other than itself, so the borohydride has to be negative, where the boron's surrounded by 4 hydrogens, so its negative charge on the boron can't get out. So it's really through the hydrogens that we use the reactivity of the negative charge. The boron's inside, hydrogens are on the outside. They can use the negative charge. So we have our tags, plus and minus. What we do then is we just dive out with the borohydride, where the hydrogen is delivered through the BH4-. The borohydride is delivering a hydride. It's in the name, borohydride. So we really treat this as delivering a hydrogen with its electrons, a hydride, borohydride. Hydride is H with a negative. So we're just delivering it through the BH4. An aluminum hydride, we're delivering the hydrogen through this aluminum hydride. So always think when you see BH4- or AlH4-, think, oh, what I'm delivering is an H-. I'm delivering it through this anion. It's being delivered. They usually act as nucleophiles because they're in these forms. They usually act as nucleophiles towards the carbon in the carbonyl. So I deliver, it's not shown here, but we have a hydrogen now that's bonded here. 1, 2, 3, 4. 1, 2, 3 things off of it. We delivered the hydrogen through the borohydride, and this H comes from the ethanol or water. The solvent provides that hydrogen that's off the oxygen. The one that's on the carbon was from the borohydride. We can use a water ethanol solution to actually hold and be present with the sodium borohydride, but because aluminum hydride is much more reactive, you can't stop that hydride that we want to deliver to the carbon. You can't stop it from acting as a base if you tried to add water or ethanol to this solution. It would go after the proton. So we want it to go after a carbon. We have to keep these things dry. We have to keep it dry. That is, no water, no methanol, no ethanol. If you do have that present, it'll just take the proton from water. The hydrides, if they're present with water, could act as a base and leave us whatever that metal is that we have as a positive charge, leave us with the metal hydroxide. The reactivity of these is a little lower, so you don't have to worry about having them in the presence of water. The reactivity of the hydrides from aluminum are a little higher, so they'll tend to react with any water or any I can't think of the word, but protic solvent. Any protic solvent, it'll take a proton from that oxygen and make hydrogen gas. So we have to keep them dry. Take-home message: lithium aluminum hydride delivers the hydride to the carbonyl as long as you keep things dry. No water, no alcohols in the same solution with this. And then do a separate day's reaction to work up the intermediate, where this would have a negative charge. We can cap it with a proton in the second day. Sort of like the Grignard reagent. We had to, in the case of the Grignard reagent, make the alkoxide and then work up with acid. We would make the alkoxide here and then work up with water to put this proton on. Alright. Let's stop with the mechanism here and we'll be done. We can take lithium aluminum hydride, that should be lithium aluminum hydride, Al, lithium aluminum hydride. We know that delivers H-, so we want to put that above the top. We know that if it's dry, it goes to the carbonyl, and we kick that up. We start creating hydrogens connected to that carbon, and we're going to get 2 with this one. This is a complete, we're just going to show the complete reaction. And this proton, again, doesn't come from the hydride. The one bonded to the oxygen comes from the solvent, if it's borohydride, or a separate day's workup from water, if it's the aluminum hydride. Those two, aluminum hydride, we had to have these separate. So 1 and a 2 punch. So we can also do the same reaction with carboxylic acids. Please know that. You can just have the same products. The alcohols, same exact products. If we use carboxylic acids and lithium aluminum hydride, also reduces to an alcohol. This is just an alcohol now. Let's show that partial mechanism. So I have the aluminum hydride, and I'm delivering again the hydrogen here, delivering that through the aluminum hydride, but I'm really going to just take the H- and attack. So I do that. I have a negative charge on this oxygen. What we can do, since this is a potential leaving group, is I can kick that off, that RO-, kick that off, reestablish the carbonyl. There's our one hydrogen on, and we can have a second hydrogen as hydride come in, and I apologize, this arrow should have been shown subsequent to this arrow, because we can drive in a second equivalent of hydride on a aldehyde. This is a faster reaction than the hydride attacking an ester. Esters are less reactive than aldehydes. So aldehyde, which is what we have here, can react with another equivalent of aluminum hydride in solution to make not our final alcohol, but our alkoxide. So we now have our final, alkoxide form that we can't do anything more with this in the aluminum hydride solution. So where does the last proton come from that's on this oxygen? That's right, it comes from the water workup. We would be done with our first day's reaction and then just work up with water and put the proton from water right here. All right, why is that aldehyde here more reactive than the ester? Well, because we know the OR group is donating to this carbonyl. We know it's a electron donating group. It can donate by resonance, our favorite word. It can donate by resonance, whereas the hydrogen or the alkyl group cannot. So this would be more reactive. I'm just going to put it down here. So it's more reactive. This would be less reactive. And that's fitting to what our order of reactivity was we started with. We said that I'm trying to find it here, ester is less reactive than the aldehyde. Now we know why. It's because that ester has electron donating effects. The lone pairs on the oxygen can dive down and satisfy the carbonyl. And if you reduce the partial positive charge of this carbonyl, you reduce its overall reactivity. So that's important to remember, this order of reactivity. So we can say, oh, this is a slower reduction, the ester going to the aldehyde, but the aldehyde going to the carboxylate is a faster reduction. That's it. Bye-bye.